Okay, today Nicoletta's second talk starting, so go ahead.
Okay, thank you. Okay, so today I would like to discuss the relations between SKT matrix and other geometric structures on complex manifolds. So again, the setting is complex geometry, so let me recall what we saw yesterday. So we have a complex manifold, MJ, this is a complex manifold. So we said that it's a pair where we have M that is a smooth manifold of, let me say, real dimension of M is 2n. And J, we said J is an endomorphism of the tangent bundle that squares to minus the identity. This is an almost complex structure. So we add an additional condition that is called integrability condition that ensures that locally we have holomorphic coordinates, okay? Okay, so we are talking about Hermitian matrix, so we fix an Hermitian matrix. G is an Hermitian matrix that is nothing but a Riemannian matrix. So G is a Riemannian matrix that is compatible with J in the following sense. We have that G of Jx, Jy is equal to G of xy for every x and y vector fields. Okay, so J acts like an isometry. And so whenever we want to have an Hermitian matrix, we can associate the fundamental form that we call omega that is defined in this way. So omega of x and y is by definition G of Jx, y, where again, x and y are vector fields, okay? So this is a two form. And in fact, it's a 1-1 form. So one of type 1-1 with respect to the bigrading induced by the complex structure, and it's real and positive. Okay, so an Hermitian manifold is given by a smooth manifold, a complex structure J, this Hermitian matrix G, and the fundamental form omega. Okay, so this is an Hermitian manifold. So we said that if omega is closed, which means that we have a non-degenerate two form that is closed, so we have a symplectic structure, we call the metric Kähler. But the Kähler condition is very strong. Okay, we said that if you have a Kähler metric on a compact complex manifold, you get a lot of restrictions on the manifold. You have very strong topological restrictions on the manifold. And so there are several ways to weaken the Kähler condition. And one of these is to say that omega is not D-closed, but it's DDC closed. Or equivalently, omega is Delder-bar closed. And this is the definition of SKT metric, okay? Where the operator DC, if you remember, is given by minus J minus 1, dj. Or here, the operators del and del bar are just the 1, 0 and 0, 1 components of the exterior derivative, okay? Because we are on a complex manifold, so the exterior derivative splits in two other differential operators of type 1, 0 and 0, 1, okay? And of course, every Kähler metric is SKT, but the converse is not true. For instance, yesterday, we saw an example in dimension 3 of the product of S3 times S3. That is an SKT manifold that admits no Kähler metric. Actually, it doesn't admit any symplectic structure, S3 cross S3. And we also saw that every compact complex surface admits an SKT metric, so they always exist in dimension 2. We saw that we have a characterizations for their existence in terms of currents. And at the end of the lecture yesterday, we saw that we cannot construct new SKT manifolds using deformations of complex structures. So that's what we saw yesterday. But in fact, in non-Kähler geometry, so when you work with complex manifolds that in general are non-Kähler, you can find other special Hermitian metrics, not just SKT metrics, but in fact, in the literature, you can find a lot of interesting papers concerning special Hermitian metrics that are non-Kähler, okay? And one of these metrics is the so-called balanced matrix. So in this first part of the lecture, I want to talk a little bit about balanced matrix, and I want to relate this matrix with SKT matrix. Okay, so this is the goal of this first part of this talk. So let me recall the definition of balanced metric. So here is the definition. So an Hermitian metric let me call the metric omega, okay? We can call omega itself Hermitian metric. So an Hermitian metric omega on Mj, where M has complex dimension n, or again, if you want real dimension, the real dimension of my manifold will always be 2n. So an Hermitian metric is called balanced if d of omega to the power n minus 1. Okay, so you take omega, you take the wedge product of omega with itself n minus 1 times, and you apply the exterior derivative, then this is 0. Okay, so these are balanced metric. A first remark. Okay, so first remark. So the balance condition, so omega is balanced if and only if omega is co-closed. So this star of omega is equal 0. And this is because the operator this star is defined as minus star this star, where star is the Hodge star operator, okay, that we saw yesterday. So, and also, okay, sorry, also star of omega is equal to omega n minus 1 over n minus 1 factorial. So you see that having d omega n minus 1 equals 0 is equivalent to have the star of omega equals 0, because the star of omega is exactly omega n minus 1. And so here you are left with d of omega n minus 1, okay? So the two conditions are equivalent. And also, equivalently, we have that the Lie form of the metric, so theta, is actually 0. And this is because yesterday we saw that theta is exactly defined as j of the star of omega. So theta is the Lie form of the metric. So every time you have a metric, omega, you can define this one form. And so balanced metric are those forms whose Lie form is equal to 0, okay? Another possible definition of Lie form was that d of omega n minus 1 is equal to theta wedge omega n minus 1, okay? So every time you have a metric, you have this equation. When theta is 0, this means that the metric is balanced, okay? Another remark is that, of course, if omega is scalar, it means that omega is closed, so every other power of omega will be closed. Okay, so in particular, omega is balanced. Okay, because again, I'm saying that every power of omega is closed, in particular, the n minus 1 power will be closed. And also notice that balanced metrics on complex surfaces. So complex surface means that we have a complex manifold of dimension 2, complex dimension 2. So of course, this condition, having d omega n minus 1, when n is equal to is equivalent to say that d omega is 0. So balanced metrics on complex surfaces are Kähler. So what does it mean? This means that genuine balanced metrics arise from starting from dimension 3, okay? Because in dimension 2, they are exactly Kähler metrics by definition. Okay, so balanced metrics have been heavily studied in complex geometry. In the literature, really, you can find a lot of papers with very interesting results about these metrics. Of course, I don't have time to, give an overview about these metrics. So let me just mention a couple of important results about balanced metrics on complex manifolds. So the first one is a theorem due to Michelson in the 83. So Michelson wrote a paper fully dedicated to balanced metrics. So actually, probably it's the first paper that is that concerned just balanced metrics on complex manifolds. But before Michelson, already Goduchon studied balanced metrics on complex manifolds, and Goduchon called balanced metrics actually quasi-Kähler metrics. So you can find different names for this type of metrics. But anyway, Michelson proved the following result that is the analog of the result that we saw yesterday for SKT metrics. So Michelson proved a characterization for the existence of balanced metrics in terms of currents. So let me just write down this characterization. So a compact complex manifold Mj admits a balanced metric if and only if M carries no positive currents T of the degree 1, 1, such that T can be written as del of S bar plus del bar of S, where S is a current of the degree 1, 0. So it's a 1, 0 current. Okay, so this is the analog of the result that we saw yesterday by Egidi for SKT metrics. There is a similar result due to Harvey and Lawson for Kähler metrics. So you see, I don't want to stress now on the specific condition for the currents here, because we do not need this result in the following. But I just want you to just have in mind that we are able to characterize the existence of balanced metrics in terms of non-existence of some special current. Okay, so why it's useful, this result? Because using, thanks to this result, you can understand whether your manifold admits a balanced metric or not. Because if you are able to, if you have a compact complex manifold, and if you are able to exhibit a current with these properties, then you know that your manifold does not admit any balanced metric. Okay, that's how this result is, that's why this result is very powerful, okay? Okay, just let me do one remark before giving you the following definition. Since yesterday, I talked a little bit about products of other spheres. So they are called Calabi-Ekman manifolds. So they are products of odd spheres. So let's say S2P plus 1 times S2Q plus 1. And we saw, for instance, that S3 times S3 has an SKT metric. But in general, Calabi-Ekman manifolds in any dimension have no balanced metrics. Okay. So if you want to find examples of manifolds with balanced metric, you cannot look at products of spheres. Okay, you will not find any balanced metric there. Okay, so this was just a comment. Okay, so before stating the other, let's say the second important result about balanced metric that we're going to see today, let me first recall a definition. That is the definition of modification between complex manifolds. Okay, suppose that you have, so M and N, suppose that they are complex manifolds. A modification F from M to N is a proper holomorphic map such that there exists a nowhere dense analytic subset S contained in N such that the map F restricted to M minus F minus 1 of S to N minus S, this is a biholomorphism. Okay, so what is a modification? So a modification is proper holomorphic map such that outside, let me say, some exceptional set that I call S, we have a biholomorphism. Okay, so actually, so somehow you modified your manifold just in this special set, because outside, actually, your complex manifold is exactly the same from the holomorphic point of view. Okay, so this is a modification. If you're familiar with the construction of a blow-up on complex manifolds, blow-ups are particular examples of modifications. Like a blow-up in a point means that we replace this point with the exceptional divisor that is a projective, complex projective space. So, but outside of this, exceptional set, you have a biholomorphism. Okay. So why I introduced this this definition? Because there is a very famous theorem of Alessandrini and Bassanelli in 93 that says that the existence of balanced matrix, so of this special matrix, is preserved, let's say, along these modifications. So let me state this a little bit better. So suppose that you have and N two compact complex manifolds. And suppose that we have F from M to N, a modification. Then M is balanced, which means for me that M admits a balanced metric. Okay, so this means that M admits a balanced metric. So M is balanced if and only if N is balanced. So if and only if the manifold N admits a balanced metric. This is not true for Kähler metrics. Actually, if you have a modification and one of the two manifolds has a Kähler metric, it doesn't mean that the other manifolds admit Kähler metrics. But what is true is that that manifold will admit a balanced metric because Kähler metrics are balanced. And so the modification preserves the existence of balanced metric. And this theorem was proved by Alessandrini and Bassanelli using this characterization of Michelson in terms of currents. okay? So somehow, so let me do this remark, okay? So let's say that in particular, since every Kähler metric is balanced, modifications of Kähler manifolds are balanced. So this is also suggesting that, you know, we have a way to construct new examples of balanced manifolds. You start with a manifold with a balanced metric, you construct a modification, and you find a manifold that still admits a balanced metric. Okay, and so in particular, so hence, the so-called, let's say, Moisheson manifolds and manifolds in class C of Fujiki are balanced. So Moisheson manifolds are modifications of complex algebraic manifolds. Complex algebraic manifolds are always scalar because complex algebraic manifolds are always scalar because you can embed them in the complex projective space. But the complex projective space has a natural scalar metric that is the so-called Fubini-Studi metric. So, and then you can restrict the Fubini-Studi metric to submanifolds. So complex algebraic manifolds are always scalar. Are always scalar. So Moisheson manifolds in general are not scalar. The theorem of Moisheson is saying that when they are scalar, they are algebraic. But in general, Moisheson manifolds admit balanced metrics. And manifolds in class C of Fujiki are exactly modifications of, so in general, are more general than Moisheson manifolds. They are modifications of Kähler manifolds.
There's a question in the chat.
Okay.
Does the modification theorem of Alessandrini and Bassanelli hold also in the SKT case?
Oh, thank you for the question. So actually, it doesn't. What is true? So what is true in the SKT case? Okay, so if I have an SKT manifold, and I have, so let me say, M is okay, let me say this. So M is an SKT manifold. And if I take a compact complex submanifold of M, okay, compact complex submanifold, then the blow up of M along N, that this is a new manifold, okay? And in fact, it turns out that this new manifold, let me call this M tilde. This is a particular modification, okay? So this is a particular modification. There is, because essentially outside of an exceptional divisor, you have that M tilde minus this exceptional divisor to M minus N. This is a biholomorphism. And E, that is E minus 1 of N, can be seen as the projectivization of the normalized bundle of n inside M. So this is a particular construction of blow-ups. So if you start with your manifold that is SKT, you take a submanifold and you construct this new manifold that is the blow-up. This blow-up manifold is still SKT. This is a result due to Fino and Tomassini. Okay, so this is a theorem, okay? This is a theorem of Fino Tomassini. And in the particular case, so in the case, n is just a point. Actually, what we know is that M tilde, that in this case is the blow up of M in a point, this is SKT if and only if M is SKT. And this is again a result of Fino Tomassini. But in general, it's not true for modifications. Modifications actually are a sequence of blow-ups and blow-downs, and the problem is the blow-down, essentially. So in general, it's not true for modification, but it's true for blow-ups. And in case of blow-ups in points, actually, we have both directions. Okay, so I think this answers your question. Okay. So yeah, so somehow this also motivates why balance metrics are very special. They are preserved in both directions in a modifications, okay? Yeah, okay. So why I wanted to, say something about balance metrics in relation to Kähler metrics, in relation to SKT metrics, because first of all, we have the following theorem. So the theorem is due to Alexandrov and Ivanov. In 2001. So if you have a compact complex manifold, and if omega is an Hermitian metric, on M that is both SKT, so which means del bar of omega is equal 0, and balanced, which means that d omega n minus 1 is equal 0, then omega is Kähler. So if I have one metric that is both SKT and balanced, then it has to be Kähler. So Kähler again means omega is closed. So let me give you a sketch of the proof. Actually, the proof I'm going to show you is not the original proof of Alexandrov and Ivanov, but it's a proof due to Popovici that you can find in his book that I put in the references on the website. Okay, so assume that. So we have an SKT metric and balance metric. So the same metric is both SKT and balanced. So we want to prove that d omega is equal 0. Yeah, of course, if you have any question, please interrupt me because sometimes I don't see the chat, okay? All right, so first of all, so I'm assuming that is SKT. So del bar of omega is 0, which is equivalent, just let me recall that del and del bar anti-commute. So it's equivalent to say that del bar del is 0, del bar del of omega is 0. So I'm saying that del bar of omega belongs to the kernel of del, all right? But this is equivalent to say that the Hodge star operator of del omega belongs to the kernel of del star. So why is that? So let me explain this equivalence. So I have that, you see, 0 is equal to del bar del of omega. Sorry, here I wrote this, but I wanted to say that del of omega is in the kernel of del bar. All right, so del omega is del bar closed. But since star square up to a sign is the identity, I have del bar, here I can put two Hodge star operator, up to a sign it's the identity, this, and I have del omega. So let me put the parentheses here, right? So in particular, since this expression is 0, I can put this Hodge star operator gives isomorphism. So Hodge star operator del bar star of star del of omega is equal 0. I just applied the Hodge star operator to the previous expression. But del star is by definition minus star del bar star. And so what we have that del star applied to star del omega is equal 0. And so here is the equivalent. The star of del omega belongs to the kernel of del star. So for instance, this is another way to define, if you want, SKT matrix. These are all equivalencies. Okay, so this was the first case, the SKT case. What about the case of balanced matrix? We have d omega n minus 1 equals 0. But d is equal to del plus del bar. So in particular, del of omega n minus 1 plus del bar of omega n minus 1 is equal to 0. But this is a form of type n minus 1 and minus 1. So if I apply del, I have a form of type n and minus 1. And similarly, this is a form of type n minus 1 n. So they are separately 0. And also omega is a real form. So it's equivalent to, so the omega n minus 1 is equivalent to say that the del of omega n minus 1 is equal to 0. Okay? Because this is also equivalent to say that del bar of omega n minus 1 is 0, because omega is a real form, okay? So what does it mean that del of omega n minus 1 is equal to 0? You see, the del of omega n minus 1 is like the del of omega, wedge omega, n minus 1 times. But then you apply the Leibniz rule. So this is just n minus 1 del omega, wedge omega to the power n minus 2, because you apply del omega each time, okay? Apply using the Leibniz rule. So del omega n minus 1 is 0, if and only if del omega, wedge omega n minus 2 is equal 0. But this is equivalent to say that del omega is a primitive form. What does it mean, primitive form? Let me recall the definition. Okay. So yesterday we mentioned the so-called Lefschetz operator that is just the multiplication, the wedge multiplication by omega, okay? So a P form with P not greater than n, let's say alpha, is called primitive if L n minus P plus 1 of alpha is equal 0. Or if you prefer, this is just omega n minus P plus 1 wedge alpha equals 0, okay? So in particular, you apply this to del omega, that is a 3 form. because omega is a 2 form. So this is a 3 form. So we have exactly omega n minus, sorry, del omega, sorry, omega n minus 2 wedge del omega being 0 means that del omega is a primitive form, okay? That is exactly the equation that we have here. So in particular, we are saying that we have a balanced metric if and only if del omega is a primitive form. Why I'm saying this? Because there is a general formula for primitive forms saying that the star of del omega is equal to I over n minus 3 factorial of omega n minus 3 wedge del omega. Okay, in general, there is a formula that is saying how the Hodge star operator behaves with primitive forms. Okay, so I'm using just this formula, this general formula that gives this expression. But this is I over n minus 2 factorial del of omega n minus 2. Again, this follows from the Leibniz rule. Okay, this last equality is just the Leibniz rule, which means that the star of del omega, you see, it's del exact, belongs to the image of del. Okay, so what we have shown, we have that the star of del omega, since omega is SKT, we show that belongs to the kernel of del star. But since omega is also balanced, we have just shown in the previous line that this is in the image of del. But in this intersection, we just have the 0 form because these two spaces are L2 orthogonal. If you think about it, if you have a form, let's say alpha, that is del exact, so it's in the image of del, so it's del equal to del beta. But if you also know that del star of alpha is 0, so alpha is in the kernel of del star, you have that this is equal to del star del beta. Okay, first I'm saying the first line is this is in the image of del, and here I'm saying that alpha is in the kernel of del star. Okay, but so we have that del star del beta is equal to 0. So if I take the L2 product of del star del beta with del beta, this is the L2 product on forms. Since del star is the adjoint of del, sorry, with beta. Since del star is the adjoint of del, this is just del beta del beta. So this is the norm square of del beta, which means that del beta is equal 0, which means that alpha is 0. So in the intersection, you just have 0, okay? So what we are proving, since star of del omega is equal to 0, and star is an isomorphism, del of omega is equal to 0. But omega is a real form, so also del bar of omega is equal to 0, which means that omega is closed, okay? Which means that omega is scalar. And this concludes the proof. Okay, so if you have a metric that is both SKT and balanced, then it is scalar. It is an open conjecture due to Fino Vezzoni, the following, that every compact complex manifold admitting a balanced and an SKT metric different, okay, let me say that admits a balance, so let me call this omega 1, And an SKT metric, let me call this omega 2, also admits a Kähler metric. Let's say omega 3. Okay, so if the metric is the same, we know it's true. It's an open problem, and it is conjecture that actually, if you have a compact complex manifold that has two metrics, one is SKT and one is balanced, then there must be a third metric that is scalar. So somehow this is saying that the two conditions, SKT condition and balance condition, are somehow transversal. Okay, they can, so these two metrics cannot coexist on non-Kähler manifolds. Okay, and of course there are many evidences to this conjecture. So let me just mention a few. Of course, there are more, but it's a result of Chiose that the manifolds in class C of Fujiki that I mentioned before, they are balanced because of the result of Alessandrini and Bassanelli, because they are modification of Kähler manifolds. So they are balanced, but if they are SKT, then they are Kähler. They are always balanced, but when they have an SKT metric, Chiose proved that these manifolds are Kähler. So this is confirming the conjecture on this class of manifolds. Also, there are some results of Fino and Vezzoni on, let me say, nil manifolds with invariant complex structure. So nil manifolds, so I'm going to speak in detail tomorrow about nil manifolds, so I will not say much now, but they are quotients of Lie groups that are nilpotent and simply connected, okay? So tomorrow, so don't worry if you don't know the definition of nilpotent Lie group, because I'm going to recall the definition tomorrow. Just think that these are special classes of manifolds, and it is known that in these cases, the conjecture is known to hold, okay? And also there are other results on solved manifolds due to Fino Paradiso, and also by in case of almost a billion solved manifolds, Ottiman for a particular class of solved manifolds that are Oye-Clauss-Thomas manifolds. Also with Anna Fino and Luigi Vezzoni, we confirmed this conjecture on some special solved manifolds with special complex structures, so and so on. So I don't want to stress on this, but just so you know that in the literature there are many, evidences to the fact that this conjecture is true, but it is still open. Okay, it's still an open problem to prove this. Okay, so now let me change a little bit the topic. I mean, I still want to talk about relation between SKT metrics and other structure, but I want to leave balanced metrics, and I want to say a few words about the link between SKT metrics and symplectic geometry, or let's say symplectic structures. Okay, so this final minute, I will say a few things about this. So what is first the motivation for what I'm going to talk about? So if you have a compact complex manifold and you fix an Hermitian metric, then Stritz and Tian introduced the so-called pluriclosed flow. That is defined in the following way. It's a parabolic flow of Hermitian matrix. So it's defined this way, del T of omega T. So we have this, we're flowing this matrix depending on T in the direction of the 1-1 part of the Ricci form of the bismuth connection. So this is the Ricci form of omega t. With starting metric omega 0, the one you fix. So I will call this PF, pluriclosed flow. So what is this object, this rho? So we have, so where rho b of xy is defined as 1.5 sum of I from 1 to n of Rb of x, y, ei, j, ei, where ei is an orthonormal local frame of Tm. Okay, we are tracing the curvature of the bismuth connection. So this Rb is the curvature of the bismuth connection. So it's defined as x, y, z, w is the curvature tensor. So G of, okay. Just like yesterday, the fan stopped working. Okay, 1 second, let's see. Okay, maybe I will close this. 1 second. Okay, should work now. Okay, so G of, okay, R, B of X, Y, Z, W, and this RB is exactly what you expect. RB of X, Y, Z is nabla X, nabla Y, Z minus nabla Y, nabla X, Z minus nabla of X, Y, Z. Where this nabla is the bismuth connection that we saw yesterday. It's the unique Hermitian connection whose torsion is totally skew-symmetric. Okay, and then you have a connection, you can define the curvature tensor, and you can define the Ricci form. So these are rho b is the Ricci form of the bismuth connection. Okay, and so in the flow, we have that, so rho b is a 2 form. So rho b is a 2 form. So it has one of its components has type 1,1. So we are taking the 1,1 component of the Ricci form. So rho b 1,1 is the 1,1 component of rho b. So this flow, so you are flowing your metric along this Ricci form. And so it turns out that if you start with an SKT metric, this flows preserves the SKT condition because the rho b, the 1,1 part of rho b is Sadelbar closed actually. So this flow, so PF, let me say the pluriclosed flow preserves the SKT condition. And Stritz and Tian proved the short time existence of the solution of the flow. Okay, so if you start with an SKT metric, this there exists a unique solution for at least a small time, starting from omega 0. In particular, notice that if omega 0 is scalar, so if your starting metric is scalar, then actually this omega t is the unique solution to the Kähler-Ricci flow. Okay, to the standard Kähler-Ricci flow. But in general, you can start this flow with a metric that is non-Kähler. However, the equation to the pluriclosed flow And let's define an Einstein-like condition for the SKT matrix. So let me recall this definition due to Stritz and Tian. So an SKT matrix is called static if the 1-1 part of the Ricci form of the bismuth connection is a multiple of omega. So you see, this is an Einstein-like condition. Of course, if omega is scalar and static, then it is scalar Einstein. Because if it is scalar, it means that the bismuth connection coincides with the Chern connection, which coincides with the Levi-Civita connection, okay? The Kähler condition is very strong, okay? All the connections coincide because you have no torsion. And so this Einstein-like condition becomes the standard Kähler-Einstein condition when your matrix is scalar. And Stritz and Tian proved the following proposition. So if MJ is a compact complex manifold and omega is static, which means that satisfies the equation you see at the top of the slide, with lambda different from 0, then omega is actually equal to capital omega 1,1. So it's the 1,1 component of omega that is a symplectic form taming J. Here is the relation with symplectic structures. So the symplectic form taming J means that omega of xjx is positive for x different from 0. So if you have a static matrix or an SKT matrix that satisfies that bismuth-Einstein condition, then actually this matrix is the 1-1 part of a symplectic form, taming the complex structure because of the positivity of the matrix, in fact. So just a remark, if omega is static with lambda different from 0, and suppose that you know for some reason that the Ricci form is already of type 1,1. This in general is a 2 form, but maybe you know for some reasons that this is a 1,1 form, then actually omega is scalar Einstein. Because in general, if lambda is different from 0, and you have the static equation, if you see omega, if lambda is different from 0, is 1 over lambda of rho b 1,1. But if you know already that your form is of type 1,1, this is 1 over lambda of rho b. And the Ricci form of the bismuth connection can be proved that it's closed, always closed. So this means that if lambda is non-zero, that you can do this, and so d omega is 0. So omega is scalar, and in particular, it's Einstein because it satisfies the static condition, and so it is scalar Einstein. Okay. Just a remark that there exist examples of static matrix with lambda equals 0. Okay. For instance, the Hopf surfaces. Again, this follows from Stritz and Tian. Okay, so more precisely, so I want to say a few words about this proposition So since a symplectic form omega is a Taming form for J, if and only if the 1-1 component of omega is positive, definite, we have the following definition. An Hermitian metric omega on a complex manifold M is called Hermitian symplectic So this is a new definition of special Hermitian matrix. So an Hermitian matrix is called Hermitian symplectic, let me say HS, if omega is the 1-1 component of a real D-closed 2 form omega on. Okay. So let me give you a lemma that show that an equivalent condition to this Hermitian symplectic condition that is mixing having a Hermitian metric that is in fact the 1-1 component of a symplectic structure. So if Mj is a compact complex manifold, then the following are equivalent. First of all, omega is Hermitian symplectic if and only if there exists a rho, a 2-0 form on M such that del rho equals 0 and del bar rho plus del of omega equals 0. So omega rho is del close, sorry, and del bar rho is minus del omega. Or equivalently, there exists a 0-2 form such that del bar rho is 0 and del rho plus del bar omega is equal to 0. It's that just the 2 and 3 are equivalent by conjugation. And this result, sorry, I forgot to say this result is due to Enrieti Finovezzoni. See, so we have an equivalent condition to the Hermitian symplectic condition in terms of the existence of this 2-0 form. As a corollary of this, we have that, so suppose that you have an omega compact, so Mj omega compact Hermitian manifold. Here the relation with SKT geometry. If omega is Hermitian symplectic, so it's the 1-1 part of a symplectic form, then omega is SKT. So it's a stronger condition being Hermitian symplectic. And Hermitian symplectic structures, we said, are born naturally from, let's say, considering an Einstein-like condition for the pluriclosed flow. The vice versa, in general, is not true. We can have SKT matrices that are not Hermitian symplectic. We can have SKT matrix on manifold with no symplectic structures at all. But the converse is true if we add an additional condition. If M satisfies the Delder-Bar lemma and omega is SKT, then omega is Hermitian symplectic. The Delder-Bar lemma is a cohomological condition. Okay, this is a cohomological condition. I will not really talk about this condition. You can think of it saying that on every form, the kernel of del intersected with the image of del bar is equal to the image of Delder bar. This is one possible definition for the Delder-Bar lemma. So let me just prove the first one because we are interested in SKT matrix. The second one, the second statement is, I mean, it's easy to prove, but it's a bit long. So let me just prove the first one, because if omega is Hermitian symplectic, by the second condition in the lemma, we have that Hermitian symplectic is equivalent to say that del of omega is equal to minus del bar rho. So del omega is equal to minus del bar rho. And so del bar of del omega is equal to minus del bar square of rho, but del bar square is 0. And so omega is SKT. Okay, very easy. So I want just to conclude with this proposition saying that if omega is a compact complex surface, we have that omega is Hermitian symplectic, meaning that there exists an Hermitian symplectic metric if and only if M is Kähler. So M admits a Kähler metric that will not coincide with the Hermitian symplectic one, okay? It will be a different metric, but you have a Kähler metric. So in dimension 2, for surfaces, we cannot find non-Kähler Hermitian symplectic structures. In fact, it is an open question of Stritz and Tian. So this is still, as far as I know, this is an open problem to find non-Kähler examples of Hermitian symplectic metrics. So do there exist non-Kähler Hermitian symplectic complex manifolds with complex dimension of the manifold, of course, not 2, okay? So in higher dimension, this is still an open problem. It is known that in particular cases, so the answer is no on nil manifolds with invariant complex structures. And this is due to Henriette Finovezzoni. And also the answer is no on a completely solvable Sold manifolds. Completely solvable Sold manifolds. So that these are particular classes of manifolds, okay? And this result is due to Fino and Kazuya. Okay, but the general answer to this problem is not known. And yeah, so I will stop here. So tomorrow we will see what Sold manifolds and nil manifolds are in details, okay? And we will discuss the existence of SKT matrix on the special class Sold manifolds. Okay, thank you.
Great, thank you very much. By the way, tomorrow we are giving a break.
Sorry, tomorrow,
Yeah.
You're right, on Thursday.
On Thursday, yeah, just.
Thank you, right.
All right, any question?